So this is what the alarm will sound like, and just so that you faculty know that your time's up, I'll stand up and hopefully you'll finish up, and then we'll get the next person up. And if just as a recap, if you can also just go on to Zoom, share screen from your laptop, so we won't have to do swap overs. Hopefully we'll be able to get through everybody quickly. Next week, we'll have another 8 speakers for another set of 8 faculty. So be ready for that. Okay, let's jump into things. Anything else I should say actually before? It looks like I've got an extra minute. Okay, so my lab, we call it Mod Lab. So I'm gonna give you just a quick one slide for one project, and there'll be 8 slides, so 8 projects. In my lab, we are a little bit more hardware focused compared to most of the other professors in the other labs. So these will be the hardware focused. There are a couple other less hardware focused projects, but for now, I'm just going to talk about the hardware focused ones. Recently, a couple months ago, we got an NSF contract to build humanoid robots. So this is a $5 million contract for 5 years with Oregon State University and Semio. The project is to build 50 humanoid robots and distribute it among human-robot interaction researchers around the country. And part of the idea is that this will give the community a common platform, so they can base their research and be able to compare research as they develop things. So this is actually Corey. The robot's called Corey. This is our second version. And so the half of the project is to develop this community and have a sustainable community for ongoing from there. Our job among the group is primarily to deal with the engineering firm that we've hired to do the development and of the actual humanoid robot, the hardware. This first year is actually mostly administrative because there's a lot of things to get started before the robot is distributed. Another robot that we have is called the Variable Topology Truss robot. So you can see it here. Essentially, the main component is what we call the spiral zipper, which is a prismatic joint. Some of the things that you can do with this system includes doing path planning. One of the nice things about having prismatic joints is that you can change your size. You can become very large, or if you come up to small obstacles, you can become very small and squeeze through them. So we have a variety of projects with this. So it doesn't always work 100% correctly. Let's see if I can get rid of this. Oh, sorry, wrong button. Okay, so another project that we've just started, we just got confirmation that we have won this grant, but they are currently in negotiations, so I can't actually mention who the sponsor is. But what we're doing is we are building. Sorry about this. We are building robots. How do I get rid of this? We are using, okay, so you can't see it. We are building a system where we have existing robots, so a Husky, Rex, and this is a ghost robotic legged dog. The idea is to do extreme locomotion. So can you build a robot system where they can go through very extreme terrains, like getting stuck in the mud or in soil or going through holes and that kind of thing. So the idea is that we use this spiral zipper arms that I showed previously in the VTT, that 2 will be mounted on each robot, and they can reach out and grab onto other robots. And then if they get stuck, one can pull the other one out, or they can build a truss system so they have a larger system that can crawl over hills and that type of thing. So this is with Cindy Sung, who will talk next week, and Doug Gerald-Mack, who's a more of a soil scientist. We also have the smallest flying robot in the world. This is what's called Piccolissimo. You can see it flying here. It's about 1 inch. We are currently working on understanding better how to do low Reynolds number flight. When you have something really small, the getting efficiency is difficult. So we're trying to understand that. Also, we have shown XYZ control for a larger version. We're trying to see if we can get that XYZ control for our smaller versions. We currently, it's about an inch long, and we're seeing if we can get it smaller than that. Also, we have an NSF project that's nearing the end with Michael Rubenstein at Northwestern, where the plan is to build 200 of these robots. These are larger version. They're about 3 inches. The idea is if you have 200 of them that can form a shape, can you have it interact? Because they're so small, they're safe. Can you have it interact with a person a person can kind of shape the global form of the swarm? We're also trying to understand the aerodynamics. So one of the problems is that the downwash from one vehicle will cause problems for the ones underneath it. So can we develop aerodynamics that can make it work well? Another project is a s'mores project. We have a bunch of master's students working on developing another version of this. This is an older system where the robots can dock together to form larger systems. They use electropermanent magnets to dock or undock. Once they form larger robots, you can do a variety of things. It's very versatile. So we're trying to do a second version where we're focusing more on specialized modules to do things like help climb onto a desk or type at a keyboard or that type of thing. We've got a couple soft robotics project. Greg Campbell is one of my PhD students who's working on focusing on, can we get a robot system that can move people around? And so how do we do that? He's currently looking at the balloon instability and trying to model that for generic soft pneumatically driven robots. Jessica Yin is working on more of a soft sensor. So this is a system where you have a proximity sensor that can see objects, but it also has a tactile sensor at the same time. The proximity can see through the soft membrane, and then the soft membrane can also, you can see when it interacts, and you can extract what the forces are between the manipulator and the robot. This is also a event camera-based system where theoretically, when you can identify the robot, the objects that you make contact with by the deformations. All right, so this is the last slide, I think. We are working with Mark Miskin, who I think will also talk next week. So he has designed these micro robots. So this is basically 3 years old, 80 microns across. You can build thousands of them at the same time. This one goes forwards and backwards mostly, and that's all. I mean, just goes forwards actually, and it kind of doesn't necessarily go straight. But the idea is, we're trying to extend that to do the locomotion modeling. Can we understand how it moves? Can we get a design which can turn, go backwards, and we can control where it goes? Also, we have an NSF grant where, with a collaborator at University of Michigan, we're actually putting a microprocessor onto this chip, onto this tiny robot. When you have something so small that works with just nanoamps of power, of current, and very, very small power, you are very resource constrained. So the interesting thing is there are only 32 bytes of memory, program memory for this robot. You know, not like 32 gig you have on your laptop, or 32 meg or 32K, it's 32 bytes. What can you do with 32 bytes? Maybe you can tell to turn once or twice, and maybe you can read a sensor. But this type of very, very constrained system program, you know, but if you have 1 million of them, you might be able to do some interesting things. So that's it for me. Next up is Pratik.
Hello, good morning. I am Pratik. I work on two main things, as you can imagine, robotics and learning, and I'll tell you a tiny bit about both of them. It began for me personally about 10 years or so ago. We were building things that look like autonomous golf carts in the campus of the National University of Singapore. And this was kind of a very grunge project. You put a little CPU behind a LiDAR on a golf cart and try to make it go around. But it was one of the first systems of its kind that looked like Uber, where you could call this thing on your phone in different parts of the campus and have it pick you up and drop you off in some other locations. Over the years, it went into this company called Autonomy, where we were building autonomous cars. They now operate in Singapore, in Vegas. If you go there, you will be able to ride in one of these algorithms that we have built, Boston and LA. And the big problems that we were solving back then was how to drive safely in urban environments. You and I, when we drive, we conform to the driving manual. And we often break this driving manual when it suits us. You speed up a little bit because the other car around you on the freeway is traveling a bit faster. We would like robots to understand when to break rules and when you shouldn't break rules while still remaining within some blanket of safety. So these are the kind of things that we were trying to do. Yeah. These days, we are interested in unstructured terrains. And so this is a project that Vijay Kumar and I have together, where we are interested in building large maps of things like forests. So think of a 2-3 square kilometer region, trees, foliage, shrubs on the ground, funny branches in the top. And we would like to understand these kinds of scenes that do not have any structure a priori. Why do we care to do this? Well, this is a project also with some forestry scientists. They are interested in things like how many trees there are, how much biomass is captured by the shrubs on the floor of the forest. If the branches of a tree branch out too quickly, very close to the ground, then that means that the trees are starved for sunlight. So these are the kind of things that feed into models of forests. Timbering industry would like to know how much wood there is. So some other people in the industry would like to know how to price carbon offsets that companies buy when they run their data centers. So these are the kind of problems we are interested in solving. And I'll show you a couple of examples. So this is not a video from our experiments. Incidentally, this is a video by Fernando Cladera, who is a student in Vijay's group. And he ran this experiment in this place called West Point, which is a university. And what I want to show you is we are doing LiDAR-based odometry across really very large regions, 4-kilometer, 3-kilometer kind of loops. And after traveling for such a long time in this environment, we can get drifts that are as small as 5 centimeters or so. We are also doing similar asking questions about how to navigate in indoor environments. There are different challenges in indoor environments. You don't have as much space to move around. You cannot always fly at the top because if you're trying to find an object, it might be somewhere hidden behind a couch. And you have a very different set of problems. Okay? Just to give you an example, so this is on the left-hand side, you see a map created by some LiDAR data. And in this case, we were interested in measuring the diameter of the trees in the forest because so people would like to back calculate the amount of the volume of wood, let's say, that they would get if they cut this part of a forest. Shouldn't be alarmed by this. Most of the forestry in the US is treated a little bit like agriculture. So these are forests that are grown by farmers in order for them to be able to cut down for 5 years, and then they'll plant it again, and then wait for 5 years. This is how wood gets made. And so we felled these trees in January after collecting this data a couple months before that. And so what you see on the right-hand side is these collaborators of ours from Virginia Tech measuring the tree with their methods. And so we can compare how well we can estimate the diameter and the geometry using drones against what they measure. That would be called ground truth. And we can get accuracy that is about 1 centimeter or so, which is very good. Okay. The challenges of these problems are mostly to do with funny sensing and funny and difficult mobility. So on the left-hand side, you see a picture from not a very complicated part of a forest. It is difficult to move around because there is a lot of structure that you don't know a priori. On the right-hand side, you see an image in broad daylight from the camera. It is very difficult to do computer vision for such images because you have very hard shadows. Okay, and that is really what we are struggling with right now. I wanted to show you this funny experiment that Siming He, he's somewhere here. He ran over the summer. He built a little rig where you put a LiDAR and then you carry it in a backpack. Incidentally, this is how like some of the first Google Maps were built 25 years ago. So if you've seen the Eiffel Tower on Google Maps, it was built because some guy took up a rig like this and climbed all the way up. Swimming did something similar. So this is Benjamin Franklin's statue on Locust Walk. And so this is a NERF. These are models that create a photometric and geometric reconstruction of the scene using multiple images of objects like this. And this is the experiment that he ran just as a fun thing. We are mapping trees on the Penn campus, and this is just a part of that. Yeah. The second thing that I work on is deep learning. And we are interested in asking two specific kinds of questions. The first one pertains to why is it that we can train neural networks very well? So these are theoretical questions. And the idea is that we know neural networks are very large. They're trained on lots of data, and they're also trained with complicated objective functions. Mathematically speaking, it shouldn't be possible to even fit a neural network. But obviously, that's not true. You can fit it very well. And the second question that we are interested in answering is why do neural networks work well on new data? In high school, people told you that if you have 10 data points, you shouldn't fit a 15th degree polynomial to these 10 data points. In deep learning, we love doing this, and we don't seem to get hurt. So these are there are applications of these questions, and I'll skip them. You can talk to me later, or there's a research statement on my website that you can read to find out more about these questions. And I will end with this picture, which is some of the students in the group. Thank you.
The fruit fly, in order to do some amazing stuff like landing, consumes only very few microwatts. And all this performance, this amazing performance in biological systems is far from what can we achieve, even with the latest generative AI in terms of really efficiency. So I will show first a few of the main problems we have worked in the past. This is our latest papers at ICCV on inferring the shape and the pose of 3D humans. This is already has really tens of applications in sports, entertainments, and medicine. We extended that. This is work by Yufu Wang, both the latest on 3D humans as well as the 3D shape of birds, where we study at a place close to Perch in Pennovation in collaboration with neuroscientists how birds actually react to the songs of the other birds based on their posture and how do they socialize, and we try to do it in a fully automated way just by having 8 cameras and 24 microphones. So another application where we really try to do it mainly based on spatial perception is vision language navigation, where we argue that the best way to follow instructions is not really to align necessarily 2D images with instruction, but try to imagine how the map is based on what you are seeing and what may be behind the walls. And based on this prediction, trying to predict a path, which you see here on red dots, based on the language instruction. So coming to the principles, you probably know that the most common neural networks are the convolutional neural networks. And at least as far as the first level of processing for perception is concerned. And while convolutional neural networks have translation invariants, they change when the picture is rotated. As you see, the input here is changing when I apply just a simple convolutional networks. And this is what we try to do with what is variant network, where we try to build features where when the input is rotated. So all the features here are rotated the same way. So if you want to have a classification, after that, you can just do a simple averaging or choosing the maximum and produce what is an invariant vector independent of the input rotation. And you can use it even for very easily actually computing directly the relative 3D pose between two chairs based just on these very powerful symmetry representations. We extended this to transformers, which have as an input point clouds like this one. And while we have, they are trained on single objects, because the objects are arranged in any possible orientation, we can still actually reconstruct the scene independent of the orientation of any object. When we want to segment the scene, we have developed a system which is really segmenting independent of the pose of the object, independent of the orientations of the chairs on this scene. And recently we have started working also on something that is very related to robotics, try to have generative models for articulations and based on this pretty much producing YAML files for robots based on some conditioning on the image, or purely like estimating the distribution of all possible articulations of objects in order to use it for object interaction. Coming back to the bioinspiration, the whole history of robotics have used cameras that are based on frames. Frame cameras were not built for robots. They were built really for photography and video and filming. Every frame is taking only every 30 milliseconds. During these 30 milliseconds, a pedestrian dashes 0.3 meters, a Formula One car moves 3 meters, a bullet moves 30 meters, and still we don't have any information during this interval. And there is a new kind of sensor, which is an event-based camera, is achieving is really a continuous sampling of the scene, though not from its color, but from the changes in the scene. And this allows us to compute the optical flow, the motion of objects, which are very fast, which you cannot even see with a naked eye, and even if the scene is really very, very dark. And this is another example where we detect in these event-based cameras independent objects. We can even reconstruct objects because of the continuity of this sensor by carving out the scene. And I think I will finish here. This is my group and the extended family of my group.
All right. Thanks, Kostas. Next up, we have Eric Eaton.
Hi, I'm Eric Eaton. I run the lifelong machine learning research group within GRASP. And imagine that we have a robot in an environment like a university, and we learn about different objects, and then we encounter something new. And then we take that same robot and move it to another environment, like a hospital, where it encounters new things like it's never seen before, like beds and patients in wheelchairs and so forth. And then we move it to yet another environment, another and another. And the idea is, just like you or I think the robot should be able to build on its knowledge over time. And so that's the motivating idea behind all of my work, that we should be able to build robotic systems that are truly versatile and learn new things very rapidly by building upon their previous experience. And they should do this over a lifetime of deployment in very complex human-centric environments. So my group's research explores these options through a couple of different areas. The first is looking at continual learning, or lifelong learning, as it's also called in the literature. And we do things like lifelong deep learning or lifelong reinforcement learning. We're also been looking recently at composable representations, building modular knowledge that can really be reused across tasks. And we do this in settings where everything is dynamic, looking at non-stationarity within the environment. we're pushing toward this idea of robotics in an open world. And so this idea of, can we detect what's new, what's novel in the environment? Can we compensate for it? Can we do this through not supervised learning or manual specification of reward functions, but instead through self-taught learning, where we can have the robot discover the objective functions that it needs to in order to improve performance? And we apply these problems to service robotics as well as personalized medicine. So as an example of what this looks like in a learning process, imagine we just have a bunch of different tasks that we're seeing over time. And on the left, you see kind of the traditional multitask learning, where notice that as it hits a new task, the performance drops. This is a result of interference. Whereas on the right-hand side, our lifelong learning algorithm is able to build on its previous experience over time, where it just gets better and better and is able to learn a diverse variety of tasks through this all this experience. And so in a robotics setting, what this might look like is we have a robot arm that starts simple by moving to a simple point in space. And then later it learns to use a hammer, and then later a door latch, and increasingly more complex tasks over time as it builds on its experience. And it just gets better and better. And one example of this is in the final thing with the coffee maker. Our lifelong learning algorithm is on the left. You can see it has to take that little cup, slide it under the coffee maker, and press the button at the same time. Whereas just if we learn that from scratch, it tends to tip over the cup as it tries to do that. And so one of the representations that we've been looking at that have been particularly effective is this idea of composable representations, where we're learning modular knowledge. So we use this idea all the time in, say, a ROS pipeline, where we have a sensor going all the way to an effector, and we connect different modules together, like for sensing, planning, acting, and so forth. And then if we have a different set of sensors and effectors, we might have different pipelines here. So these are very, very modular types of programming constructs that we use all the time, and we can combine things together into new pathways, right? We could take a planning module from a different pipeline and connect it in together. So what we've done is take the same idea and implement these as neural modules, where we're learning this, what these should be and what the parameters are for them. And so the idea is that we should be able to go end to end from sensors to effectors and be able to dynamically combine these together as needed to solve new combinations of goals. So an example of this in manipulation here, there's an arm where it's got to simply just do a pick and place task, picking up a soda can, moving it to a particular target. If I change the objective here, instead of swapping out everything, we really should just be swapping out the one module that corresponds to that new objective, that is taking the soda can and placing it on the shelf. In a larger scaled up version, we could do the same pick and place task and then generalize it out by not only doing the same task, but now changing the arm, so which might involve new dynamics here. And then we could take that and now change the objective a little bit. So now instead of picking in place, we're now sliding the object across the table. And then we take and we switch the object out to something else, like a plate. Then we can make the operation even more complex by adding in obstacles, where now it has to move around this brick wall. And as you can see, we want to build up this versatile robot that's really capable of handling any combination of things that we throw at it. And so we're moving towards this idea of lifelong open world learning, where we have different objects in the world. When we see something new, we need to accommodate this automatically. So instead of having the world segmented into tasks that we learn, we really just experience a continuous stream of observations and make sense of it. And so I'm going to talk about 3 projects in particular that we're working on currently. And if you're interested, there'll be a link at the end that you're welcome to let us know about that, and we'll reach out to you. The first is the DARPA Triage Challenge. So this is the latest in the DARPA Robotics Challenge series, and we're in the process of planning to field a team for this at Penn. So DARPA just announced an open qualification where any team can apply to do this, with the first competition in October 2024. So our general approach here, and this is a map of the Pennovation campus, is to send a series. So the basic idea is that in a disaster, first responders should kind of pull up, press a button, robots should go and survey the scene, locating all the victims and triaging their injuries so that we can prioritize first responders. So that's the basic idea behind the challenge. So we send the robots out, map the canvas using a semantic map. And then from this, we localize the victims using a combination of deep learning as well as human-aware models, creating a signature for characterizing the victim's injuries here. From that signature, we're going to be doing triage, which allows us to prioritize the first responders. And so this is a collaboration between myself, Kostas Daniilidis, and CJ Taylor and Grasp, as well as 3 MDs who are trauma surgeons. And this really combines kind of foundational robotics with navigation, perception, and multi-robot control with machine learning for clinical applications, including human vision and diagnosis and triage. The second application that we've been working on is this idea of an autonomous service robot. So I'll just play just a hint of this on there, where we have a robot that kind of goes around environments, takes pictures, and learns about it. Actually, in the interest of time, I'm going to skip ahead. So this is an example of this robot. This is a demonstration we ran at ICRA last year, where the robot was going around and autonomously mapping the environment and learning about how to do occupancy prediction around the space. Last thing is a series of medical applications, including deploying ambient AI in a clinical setting to act as essentially an assistant to clinicians, as well as doing surgery support for endoscopic surgery with Dan Hashimoto, who's also a GRASP secondary faculty member. These are my current and former students who contributed all this, and thank you very much. And if you're interested, take a picture of the link down the bottom and please let us know. Thanks so much.
Thanks, Eric. Next up, we have Nadia Figueroa.
I'm connected. Nice to meet you.
You're already on. You should be on Zoom.
Yeah, but it got disconnected. Do I appear somewhere?
No, no.
Phone?
No.
We can't use with the HDMI.
You can, I don't know if it'll work. We weren't able to get it to work the other way. It's just not connecting at all.
It's not. Let me.
Let's see if we can. No, her internet's completely down.
Yeah, I can't
Can you
connect to
email?
Wi-Fi, but then yeah, I lost.
Can we do the HDMI? Yeah, oh yeah, we have to change the. How to do it. We have to change.
Yeah. I'm going to append that.
You want to just switch and see if Dinesh will go first?
Okay, yeah.
All right, until you can get on. All right, we're having internet problems, so what happened when I closed the Zoom? So okay. Why is it here? There it is. Okay.
All right. All right. Hello, everyone. Excuse me. Hello, everyone. So my name is Dinesh Jayaraman. I'm an assistant professor in CIS. And my research group is called the Perception, Action, and Learning Group. We've recently started calling ourselves PEMPAL. We noticed the fortuitous acronym. And so what I work on is robot learning. We are interested in trying to build general purpose robots that can operate in our homes and offices and hospitals and workplaces. And that brings me to kind of my opening slide, where these kinds of environments have been found historically to be really hard for robots to deal with. If you think about the kinds of settings where robots have worked well, they're kind of more like the settings that we have on the left, right? Where we have this kind of very structured setting. And from the reactions, I can see that you've noticed the human on the right-hand side who's crossing this road in very perilous settings, apparently very nonchalantly. And these are the kinds of settings that we are able to handle as humans, but robots are very, very unable to handle them today. They're more representative of the kinds of settings like homes and offices and hospitals and so on that we'd like to be able to work in, but they're typically characterized by many unknowns and uncertainties. And so really, I like to think of these settings in terms of the information generated in the environment, and there's more information generated in the environments on the right because there are more unknowns. And so we have to think about how to handle that. So the way that I think about this is that there's information generated in the environment that's trickling down through various computational processes in the perception action loop. And it looks like this, right? So we are thinking about kind of these steerable abstractions where we want to, for example, at the observation stage, think about how do we attentively gather the right information that gathers task relevant observations for the particular task we're trying to solve. Attention also at the level of representation. How do we identify the right objects, for example, in the environment that we need to pass on to the decision-making agent? And then attention also in terms of temporal attention. How do we pay attention at the right instance, both in terms of kind of switching on or switching off more computationally intensive processes, but also in terms of attention over past data that we might have acquired, attention in the context of learning. How do we pay attention to the right portions of our past experiences to inform robot learners? So really, attention in this context is a really kind of broad term. It refers to broadly learnable mechanisms that dynamically steer these information bottlenecks to select task-relevant information. And by doing this, we're hoping to build kind of nimble robot learning loops that now have flexibilities in terms of pre-training. We're able to train these different modules with various kinds of data sources and not necessarily be restricted to robot and task-specific data. And also, we're able to build flexible task specification. We should be able to, a layperson should be able to ideally specify tasks to a robot, and then flexibility in terms of resource allocation or efficiency, right? So I'm going to talk for as long as they let me talk, but I will... I'll try to give you a taste of a few different things that are going on in the group right now, maybe one on each of these three different kind of portions of the robot control loop. So on the topic of attentive information gathering, we'll look at training robots to interactively evaluate robots. Spatial attention, we'll talk about pre-training representations and so on, right? So let me start with the first one, which is the representation stage. So what we've recently done is that we've found that we can train really good representations for robots, not by using any robot-specific data or by using task-specific data, but by instead kind of pre-training these representations on in the wild human videos. So we can take large data sets of humans performing various tasks, like the one that you see here, of which there have been a few in the last few years, like Ego 4D and so on. And these are videos that are showing humans performing purposive actions. They're trying to accomplish some goals. That gives us some information about what it means for a robot to also make progress towards achieving those goals. So that's the high level idea. And from doing this, we're able to train representations that track the progress of the human towards the task. So just by looking at, for example, a language goal that says open the microwave, or an image goal that shows a picture of the open microwave, this representation is going to give you a score for how close or how far you are from this goal that's been specified to you. Now, what's the point of doing this on human videos if you can't do this on robot videos? Well, it turns out that actually the same representations now work well on robot videos as well, because so we find that it actually generalizes out of the loop because we've trained on so much data in the wild that actually it's able to become invariant to various domain differences, and even to the fact that we have a robot agent now rather than a human agent that's performing these actions. So you'll see that in each of these cases, regardless of whether you specify a language goal, which is this column on the right, or an image goal, you're actually able to track progress towards performing the task of putting the hat on the bottle, or opening the fridge, or putting the bottle on the lower shelf, and so on. And we can use these now, obviously, to synthesize robot behaviors, robot policies. And so we find that we are able to do cool things like, for example, only provided a few tens of demos, we're able to learn a variety of tasks like putting the pineapple in the black pot. Let's see if this works. Putting the pineapple in the tray. These are all tasks in this case that are specified through a language phrase and a few demos, right? Putting the apple in the green pot, and then we can chain all of these together by saying, put all the fruits in the tray, and we can kind of get this behavior where all of these skills are chained together, right? So we find that this kind of approach outperforms several existing state-of-the-art representations for robotics. We've also kind of expanded from here to think about more object-centric representations. So, for example, abstracting a scene into various levels of key points where, for example, in this human, there are a standard way to do this would be to only look at one level of key points. But here we're looking at multiple levels, which are kind of represented by these families of key points with parents and children. And then on the right-hand side, we have this in the robot setting. Okay. I'm going to take just a couple more minutes. And so here we have another example now of attention applied to information gathering. In this context, we're thinking about information gathering for rewards, right? So what we'd like to do is, for example, learn tasks like these that are closing and locking the door. But it's hard to specify what it means to a robot to close and lock the door. The way you and I would think of it is that to have successfully performed this task, if we tugged the door handle and tried to pull it open, on the one case, we would find that the door indeed opens up, and in the other case, it doesn't. And so how do we actually use signals like that as rewards for training task policies? We found that actually we can take these kinds of evaluation behaviors, we can learn them automatically, and we can use those learned behaviors to then inform the learning of a task policy. So we have a learned interactive reward perception policy, and that interactive reward perception policy now informs the learning of an actual task skill. And so we're able to perform tasks like indeed this kind of door locking task, but also tasks like block stacking and screwing, much better than alternative approaches to specifying tasks. So I really think of this as kind of enabling a new way of specifying tasks to a robot learner that's much more versatile and much more simple than alternative approaches like, for example, using true states at training time. And we're able to then learn policies that are scrupulous in the sense that the robot essentially checks its own work. I think that's maybe all the time that I have, so I'm going to quickly skip to an acknowledgement slide. Okay. So yeah, so this is basically a picture of our group from a year and a half ago, and this is really about attention applied to different parts of the control loop. So if you're interested, please contact us.
All right, thanks, Dinesh. So we're having a very strange Wi-Fi issue. I'm going to ask if you're connected to the internet or to the Wi-Fi, can you disconnect? Because our speakers are, for some weird reason, multiple people have the Wi-Fi drop out. Maybe that'll help.
Share screen or
No, you're. Oh yeah. Is this going? Yeah.
share screen?
Yeah. Oh yeah. Wait. Okay. Wait 1 second. So, but okay, try now. Okay. All right. Jianbo Shi is next. You okay? Are you connected?
I think I am. All right. It's a lot of great talk. I enjoy hearing all my colleagues talk as well. So my name is Jianbo Shi, and actually, instead of talking about my work, mostly is my students' work. So I'm going to start one by one. First is Kate, is one of our newest students. This is collaboration with Kate and Linji, with my oldest students. So when you're this, first students, you should just try out something hard because you have the beginner's luck. So this is a topic that actually I was very interested in for a long time, but didn't dare to tell my students. So Kate actually figured it out. It's called amodal completion. And we're going to use some of the latest diffusion process. And in a nutshell, it's basically look at this painting of the son of a man and try to imagine what he looks like without the apple on his face, or even what he looks like below the frame. So Kate is going to attempt to solve this problem. And we know that we are living in a sort of everything happens everywhere. The movie, everything everywhere era, where the computer vision seems to solve every problem any 6 weeks or so. So we have this model called SAM, called segment anything, that seems to solve all the problems that I used to worry about at middle of the night. And now it's like we can just run it on any data we have. But now the question is, can we actually see a little bit more than this just objects? Can we see behind it? Can we see beyond what the image frame is telling us? So the two elephants tend to kind of go together in a social setting. Can we see from one foreground and see through the background? And can we see behind the objects? Think of it like growing plants, right? So we see the plants and, we just put the seeds on it and they just want to grow that thing out. So you forget everything. So it's just basically like a seed growing problem. If you look into the problem a little more, things get a little bit more complicated because things occlude each other because there's reason to occlude, right? So in a social setting or in a context of playing soccer, there's always a player in front of you, right? Otherwise, it would not be fun playing soccer. On the street scene, there's a social setting where cars just tend to group together. Things kind of co-occur a lot. So in order to remove the foreground object, and see through the background object. The goal is not try to include another occluder in front of you, right? So if you just let the system grow, it will grow another person in front of it, because very likely there's another person when you play soccer that try to tackle you. The other problem is image framing. Basically, the artist or the cameraman or first person try to frame something so they can focus on something. That creates a framing problem. You want to see basically how to extend beyond the image frame. So we're not trying to destroy the artist's framing, but we want to see things going beyond the frame. And that requires you to know if something is complete or not. Okay, so you generate something, you need to know if it's complete or is it half complete. The last one is called accidental occlusion, which actually is very tricky sometimes. Like little cats go into your suitcase, and then you take the cats out, and because of the indentation on the suitcase, you put other things into it. So this is not a usual occurrence, but it tells you some kind of physical occurrence of relationships. Long story short, we try to use this sort of segment everything paper, try to segment the object out, figure out the occlusion relationship, so knowing who's the foreground. We delete that foreground, right? And then we ask a computer to in-paint into it. This requires sort of contextual reasoning. We use this diffusion in-painting engine to kind of figure out what the context looks like. And then we in-paint the entire scene, and then we segment the object back out to obtain what we want. So this is look like some of the example we've seen. This man sitting on the bench, we remove his bench. Now he has a very strong core. He's just bending down, sitting there. We wonder what the car looks like. Just we generated a car on the right column, and we trim back a little bit of background. So basically, you cannot generate anything on it without context. So the context is always there, but that's your helping tool to kind of generate the picture. But once you generate it, you kind of trim it back a little bit to get rid of those contexts that you don't want. It's still a very challenging problem, particularly when you have shadows, occlusion, and so on. And we cannot get rid of the things completely. And certainly, person don't float in space unless you're Harry Potter. So you delete the horse, you get another horse back in. And the framing actually is a very annoying problem, because when system fails, it just put another frame back in there. Looks like a window that you're sitting behind. So these are realistic things, and this is what AI can do today. What we're trying to do is steer the context reasoning so that it does what you actually want to do. So skip that. The next one I would talk about Jose's work, it's called brain encoding. This is basically somehow you're like doing some task, like maybe Jose is doing Instagram or Twitter, and we have an fMRI scan of his brain, and then we try to predict what his brain is going to do. So for that, it's called brain encoding. The reverse is if I have the brain scan pattern, can we decode out what is actually seeing at the moment? So this is a picture of Hu Zhenghu sitting here. And for this, we have worked on this Argonaut Challenge 2023, which is a very nice data set that a bunch of neuroscientists had gathered together over a whole year period. And they really had done a great job, cleaning it up and send it to the community to use. And there's a reasonable small prize to give out to the winner. And somehow Jose got to a point which is ridiculous high, the first prize winner. And it's actually testimony to the community. We are actually working on with the second place winner to figure out what actually happened. I think we're not that great. So it must be something going on with the data set itself, or we discovered something interesting. So we're actually working with them closely, try to figure out what happened. So this is your brain in the full form, hopefully. And this is kind of just animating a view of your brain. If you can see, vision people start with V1, which is right in the bottom of the cortex here. And there's a higher level cortex above that. So we are trying to predict the entire brain region. And you can see the red region are the one that we are able to predict at this moment, have a high score. You can see actually we're doing pretty well across the entire brain regions. I'm going to skip some of the data. I think the main thing you want to get away with is that we actually figured out how exactly the 3D brain is mapping to the 2D images by just looking at the data they provided to us. So there's no actually ground truth of how the 3D brain is mapping to 2D images, but with the data, we are able to actually estimate quite well from V1 cell. For example, the left side of the brain is looking at the right side of the image. So the things are flipped left and right, that we know. Things are also flipped upside down. Furthermore, we actually work out the entire mapper called the retina mapper that maps every part of your visual cortex into the image domain. So the color codes indicate the 2D region, and we essentially figure out how things are mapped. So it tells you also the attention regions. So the higher cortex tend to pay attention to wider regions and then the smaller regions. Yeah. So I think I don't have time to talk much more. Just final conclusion is that we spent a whole summer. If you see me kind of sleepy, it's because I had a whole summer collecting this data set called Ego 4D that Dinesh talked about. And this is an expert edition where people actually are experts, dancers. So some of the people from Penn and some expert chefs, not exactly chefs. So we have also collected a lot of musicians doing this work. And this is a very cool project. We're wearing this new glasses made by Aria, which is a team from Meta, Facebook. We're recording from the first person. We're recording from the third person. We're also recording people narrating, talking about what they're doing. We're also recording expert commenting on how you're doing. So we have all kinds of multimodal data for you to play with. And from that, we are doing analysis of people tracking in 3Ds. We are looking at how gaze and hand interact. We know that gaze usually leads to hand interaction, and gaze usually detach before hands detach. We're actually doing some bit of a scientific discovery that the hand detachments and hand interaction has a gap about 2-3 seconds. Those are the things that we don't know. We're interested in using the data to all kinds of analysis of hands, predicting how hands can interact with objects. This is music. We're doing a hand detection, and also work with Lingjie using her Muse system to segment the hands out and also 3D reconstruct, which just 5 camera views. So I'm looking forward to get more stuff out of it. But final thing I really want to get away with is talk about is just expert when they look at interaction of activities, they see things very differently. They don't just say you're playing music. They are seeing you how actually are practiced, what technique you're using to play that piece of music. So these are 2 different players using the same technique. Looks very different, but they're actually the same type of technique. So now I kind of finally understood, activity is actually not made of things you want to do, but made of things that you could do. So you have techniques you have mastered, you just kind of work around those techniques you have. So we're going to skip that. And finally, that's the picture that Kate was working on. We take the apple off his face. So didn't put his eye back, but it looks like a realistic painting. And now we know what he looks like below his jacket. So that's it. Yeah. Thank you.
All right, thanks, Jianbo. So we're gonna again try to get Nadia on, who's syncing through her phone. So hopefully this will actually work. Yeah.
All right, trial number 2. So my name is Nadia Figueroa. I run the Figueroa Robotics Lab here at Penn. And what we focus on is on safety, adaptation, and efficient learning in the context of physical robot interaction. And what I mean by physical robot interaction is robots actually physically interacting, making contact to humans or through objects that humans are carrying, like you see in this video here, where I'm carrying this large car parts and moving it towards the workspace of the robots. And the goal of the robot is to intercept that object, right? So this is called a handover. So as you can see here, the robots are quite adaptive. They're reacting to the motion and the orientation, the location of the object. So we're doing some prediction of where the object might land, and that we intercept it and do this handover. So apart from doing these kind of like interactive handover tasks, we also focus on very reactive motions, like not just walking towards the robots and giving it the object, but actually throwing an object to the robots and then having the robot catch those objects. And so as you can see, these type of the controllers that are under the hood, it's not really like you cannot plan, right? Like this is something that has to be very reactive. We have to have very high frequency sensing, for example, being able to sense the motion of the object or predict where the object is going to land in order for the robots to react to it. And as you can see, we're also exploring now, what if the human changes the intention completely, right? Like now the robot knows how to grab the object, but then the human can grab the object, take it back. And then now we have kind of like adaptation also on the fingers, right? So you can start playing around with the robot like this. So all of in order to achieve all of these very nice behaviors, very nice kind of like interactive behavior of the robot with the human. This is exactly what we focus on in my lab. So like these three things of safety, adaptation, and learning, right? So like the videos that I showed to you before is more on like the adaptation capabilities that we seek our robots to have. And really the underlying technique to achieve this is to consider the motion that the robot has to follow as a dynamical system itself. So like as an autonomous dynamical system, right? So instead of having to plan a trajectory that the robot has to follow, we model that trajectory or an infinite number of trajectories as a dynamical system, as it could be at this first order, this function f of x equals x star. And the whole idea is that if we model the task now, the task at the motion level with this vector field, which can be represented with this dynamical system, then the robots will go to the target or will follow that trajectory from anywhere in the state space, right? So like if the target moves, the entire vector field moves. If the robot is perturbed, then it will come back to the targets or to the trajectory. And the way that we can ensure this is by using tools from control theory, right? So basically modeling the motion task as a dynamical system. And in order to ensure that it converges and that it's stable, we introduce these conditions from Lyapunov theory, right? So we have a Lyapunov function that's grounded on the target. And what we want is for our dynamical system to always be dissipating the energy and converging towards that target. So this is how we formulate the task. So for in the videos that I showed before there, we kind of like parameterize these dynamical systems just to do grasping, just to go and intercept the object. But we can also learn these dynamical systems from demonstration. If we want the robot to actually follow a specific trajectory, then what we do is, the red trajectories are demonstrations that the human gives to the robots. And as you can see there, we already introduced some formulation. The idea is that we learn this function f of x that represents the vector fields by imposing these Lyapunov stability conditions, right? So we need to learn a Lyapunov function that represents that trajectory that you're giving to the robots. And then by having those parameters of the Lyapunov function, we can impose the stability guarantees on the dynamical system. And what's cool about this is not only that we have these nice guarantees of how the robot will move. So as you can see here, the robot is perturbed and it just continues on following the path, right? Without having to do any replanning. So it's very reactive on the fly. But the cool thing is that we only need a very small number of demonstrations to learn this vector field, right? So from 1 to 3 demonstrations, we can actually learn this vector field, which will give you solutions from anywhere in the state space. So that's the cool thing about it. And here you can see a video where you were demonstrating this kind of like inspection task to the robot. I give it 1 or 2 to 3 demonstrations, and then the robot learns the vector field that reproduces that trajectory. And as you can see, I can perturb the robot while it's doing it, right? And it allows that perturbation. It allows for the human to change the task as well without having to do any high-level planning or high-level decision making or switching between what the task actually is. So this is a cool thing. Here's another example of using the same kind of like formulation where we taught the robot to follow that track on the floor, and as you can see, the robot's following it, and you perturb it, and it goes back to the track. So this is some newer work that we've been doing together with Nick Matney of imposing these stability guarantees on the Lyapunov function that's grounded on a target limits the complexity of the trajectories that we can actually represent. So here, Farhad, what he did was said, okay, why don't we treat the motion policy then as a controlled system where we learn a unstable model of the trajectory. So now we can represent periodic trajectories like this one here with a neural ODE, and then we stabilize the system using control Lyapunov function. And as you can see here, we are teaching the robot how to wipe the mannequin doing this very periodic motion, and it also has these nice properties of being able to be robust to perturbations and then going back to the trajectory. So now we convert not just to a target, but to a trajectory. So now we can express more complicated tasks. And then this is another recent work that was accepted at Coral, where now instead we teach the robot one trajectory with one trajectory to do one task, and then we change something in the task. So we completely change it. We change the target. We change the orientation of the targets. And normally we will need another demonstration to be able to learn this vector field, this policy. And with this new technique, we don't need to do that anymore, because what we're doing is we're introducing some geometric descriptions of the task into this function f of x. So all of these reproductions are without any learning. It's just adapting to the changes in the environment. I'm done, right? Or yeah, I have one more minute or no? Okay. So yeah, and here's another video of like taking this a little bit further and saying that we can also adapt to failures. So if we introduce some notion of it's not just about what the motion of the robot should do, but in this case, the inspections task is all about passing this cube through the scanner, right? So like if suddenly the perturbation of the human pushes the robot to go away from the scan, then that's a failure. So now we implemented this kind of like adaptation to failures as well, so that it can come back to do the task correctly. And here we can see also for a scooping task, like if the robot is perturbed, it drops the beans, it knows that it drops the beans, and it basically comes back and scoops it again. So we're introducing this notion of reactivity, not just at the motion level, but also at the task level. And we're now pushing it further into the force level, where we want to start thinking about tasks where the human and the robot are, for example, co-manipulating a heavy object that has a known weight. And then how do we adapt to all of these changes when the human and the robot are working together? So yeah, so that's my time. And I'm just gonna jump to my slide to show my collaborators and the students in my lab. So thank you.
All right, thanks, Nadia. So we're shifting around the order a little bit. We've got René Vidal, one of our newest. Oh, you okay? Okay. New faculty here. So hopefully the computer's still working. And then the last speaker will be Michael Posa. But first we have René. All right, it seems to be working.
All right. That was a good entrance. So I'll begin first by saying I just joined Penn, and part of my joining Penn is to be working on the new data science initiative at Penn. You've probably seen that there is a new building being built just one block from here. There's going to be a lot of faculty recruitment in AI for scientific discovery, trustworthy AI, bio-inspired computing in AI and health. And very well connected with some of our recent centers, ASSET and the Center for Data-Driven Diagnostics. About my lab, I just moved from Hopkins. This is a picture of my lab, what it was maybe a few months ago. There's 7 new students at Penn and 4 new postdocs. So the lab is, oh, it's not working? Yes, I think I got the wrong view. So let me stop sharing. Share again. And now,
Oh no, maybe the play before you.
yeah, it stays like that. I should stop share. I say first. screen. So I'll just do it like this, and I'll just share the whole screen. All right, that was the building. These were my students at Hopkins, and there are 7 new students and 4 postdocs that have just joined Penn. So welcome all of them. So my lab does broadly 3 things: machine learning, computer vision, and biomedical data science. Within machine learning, we have many areas of research, but broadly, we're working in trustworthy and explainable AI, the mathematical foundations of deep learning, interplay between optimization, learning, and dynamical systems. In computer vision, we do many things, but the major focus these days is at the intersection of vision and language, and activity recognition. And in biomedical data science, we work in many areas of medicine, but including hematology, urology, radiology. I'm also a professor in radiology at the School of Medicine for that. So a few highlights of a few projects. This is a work on explainable AI. We believe that forward is going to be extremely important to be explainable to the user as to what they do. And we believe that the current deep network technology is very obscure in their decision making. And rather than trying to explain what they did a posteriori, we're trying to develop AI systems that are explainable by design and explainable to the user in human-like language. So we play 20 question games with the AI systems where we ask questions, or the AI system is asked questions that need to be answered. And so the predictions that are made, in this case, classifying a bird, comes with a list of questions and answers as to why that prediction was made. In the theory of deep learning, we are trying to understand many of the mysteries behind deep learning, such as why, when the networks are made bigger, performance is better as opposed to worse, why we don't suffer from overfitting. And that requires analyzing the interplay between the design of the architectures, understanding the optimization algorithms that are used, as well as understanding the interplay between optimization and generalization. And I've got many students working there on theory. I did mention that in vision, we're working at the intersection of vision and language. We are in particular using large language models to come up maybe with questions about the semantic content of scenes. We're using large vision and language models to provide answers for those, and combining therefore that with visual question answering to provide the explanations that I was talking about earlier. In medicine, we work at multiple scale with multiple imaging and other sensing modalities. At the cellular level, we do work, say, in hematology, trying to do cell detection and counting to produce new blood tests. Or we do work in neuroscience as detecting cells, neurons, and the spiking activities from various imaging modalities. We've also worked in embryonic stem cells, trying to detect the spiking activities of them. At the organ level, we work on brain MRI and diffusion MRI in particular, and we develop techniques for segmentation, detection, classification of various neurological diseases. And at the surgeon or patient level, we work on understanding human skills or surgeon skills at doing surgery with a robot, or analyzing videos of children that have some diseases, such as autism or Tourette syndrome, and developing computer vision technology to help the diagnosis. Perhaps just to provide one concrete example, in this project, the idea was to reduce the time it takes to produce a blood test from, say, 5 days today to 5 minutes. The way we do that is by taking a drop of blood from a finger that goes into a small microfluidic device. In that microfluidic device, it goes into an imaging chamber that does holography. And then we develop techniques for holographic reconstruction to get high quality images. And then we develop machine learning and computer vision techniques to detect red blood cells, white blood cells, and produce the complete blood count in a few minutes. That's it. Thank you very much.
That was wonderful. Actually on time. Michael Posa is up next. Yeah, I'm gonna try to add the corner.
Oh, just make me a co-host. Yeah, yeah, yeah. But now I think you can't. You moved yourself. Oh. I know we're still a co-host here. Oh, yeah. I think because I'm not the host anymore, like I go to it. This computer is no longer the host, Jerry.
Yeah. I think Cherry's working on it. You can also plug in.
All right. While we see if this will work. I'm an assistant professor here, and I run the Dynamic Autonomy and Intelligent Robotics Lab. I can now share my screen. This is a lab photo of us from not too long ago, a couple years ago. And we, as everyone else says, we work on robots. And, you've all seen these videos, right? Things like Atlas running and jumping and the Rubik's Cube. And so the question, as a roboticist who's done this for a number of years now, comes into my mind is, well, why don't I have a robot like this in my home or in my workplace? What's sort of preventing us from actually taking these out of these settings into the real world? Instead, I do have a robot, right? It's not a robot for home, but we have a robot. And that's sort of like where we're at today. We got a real delay, huh? Yeah. All right, maybe I'll just plug in then. It's just maybe disconnected, or who knows. Yeah, I disconnected.
Weird one.
Yeah, I mean, you can just.
Oh, and you want to. But we want to put on the Zoom.
Well, I'm not sharing my screen anymore because it's not gonna. If I'm the last one, and I just present to people in the room, and we can forget Zoom.
Oh, this time it came up.
That's because I switched over. Yeah. I switched the screen over to my laptop. That's why we're seeing this. Or do you want the computer back? It was my computer disconnected again. I don't.
Right, yeah, just go ahead.
Okay. So we can. Go ahead. Okay, so we have Roombas, and so the thing that sort of I've been thinking about is if I want robots to get out of the lab and into real world settings, they're going to need to be able to handle more complicated environments, right? Not just scripted settings. And for that, I really want to think about this low data problem. I want to say robot's going to see some stuff, whether that's in your house, your kitchen, or your workplace, and it's going to need to accomplish a task in a few minutes. right? So how do we go from sort of first sight of some scene to some task completion? And we've been working on a bunch of different projects in this area, and I'll sort of highlight a few different things we've been thinking about. So one project we've had running for a little while now is on control. So we would like to do real-time control for robots that are going to reach out and make and break contact with the environment. This ultimately is a hybrid decision-making problem where it has to decide what it's going to touch, when it's going to touch, where it's going to touch it, and has to make this decision very, very quickly. Okay, so when you think about traditional gradient-based optimization, they really struggle here because the gradients don't predict useful information through things like making contact or breaking contact or starting to slide and starting to stick. And so this is like I said, an ongoing project in the lab. We've recently put this on our Franca arm. The most recent thing not shown here is we've actually been combining this now with some adaptive control and doing online learning plus control and rolling a fruit around, right? So from no real information about the fruit or how big it is, we can sort of try to touch it and eventually figure it out and start to roll. So this is real-time decision-making, a lot of algorithmic work that's integrating an understanding of non-convex and convex optimization with an understanding of the underlying physics of the control problem. We've also been doing a lot of learning here as well. And in particular, we've been thinking about physics-inspired learning, and particularly physics-inspired implicit learning. So how do we use implicit representations as well as implicit loss functions that build in some understanding of contact dynamics? Let me try to make the things scale a little bit better. Into this learning problem. So our setup right here is we're going to take an object and we're going to throw it, and we're going to record its motion. And then we're going to try to back out what that object's geometry, mass, frictional properties, inertial properties, and so on must have been, purely from watching the fact that it bounces and slides and skids. And so our first pass is this video shown here, where we can sort of compare the approach we're taking, where, you know, with 10, 20 trajectories or so, we basically figured out from nothing that it must have been a cube, just from the way it bounced and slid and rolled. And you can compare that to things like differentiable simulation, or you can compare that to things like end-to-end learning that don't work particularly well. The latest thing here, and this is a work in progress that is a collaboration with CJ Taylor, is to get rid of the motion capture, get rid of the APO tags shown in here, and actually do this all jointly from vision. So how do you take the fact that vision underlying, you know, the vision has some underlying geometric representation of the world, combine that with the fact that physics also has some underlying geometric representation, and do those two things jointly. We do a lot of Lego locomotion in the lab as well. And so just to sort of show some highlights from the locomotion, we have a Cassie biped in the lab. We've been thinking about running and jumping. A lot of the work here has focused on how to do, again, real-time control, how to think about the role of simple or reduced order models. Most recently connecting that as well to real-time vision pipeline. So how to use vision to generate train maps and then use those to plan over the train, so to walk and run and so on. And then the last sort of project I'll highlight here is thinking explicitly about model order reduction. So if I want to do control, if I want to go from the relatively simple roll the ball, roll two balls around problem to a real world, in your home task, I cannot think about everything all at once, right? There's some simpler underlying representation that we need to use to abstract away all the different information that's not relevant to any particular task. And we've been thinking about this from a control perspective and from a learning perspective, how to automatically, from data, from a notion of a task space, identify what salient information is actually necessary to achieve the task. And thinking about that both in the context of locomotion as well as manipulation. So how do you cut down on the dimensionality of the problem, or in fact, the dimensionality of the number of contact modes that you have to consider? And then with that, I'll sort of thank all the students who have done the hard work. This is unfortunately a somewhat old picture. So if anyone is new to the lab, you're not unfortunately here yet, but we'll have a new photo soon, as well as we have nice collaborators in the government and in the industry.
All right, thanks, Michael. Thanks for if you're interested in any of these projects, feel free to contact the faculty.